Welcome to this ASPIRE demonstration video in which we will demonstrate the anti-debugging technique developed by Ghent University. What are the security requirements that we try to fulfill with this protection? Well, it's confidentiality of code and data and integrity of code and data. More concretely, in this case, the requirement that we want to meet and the goal of our protection is to prevent dynamic man-at-the-end attacks. Very concretely, we want to prevent that an attacker attaches his debugger to observe the program being executed and its memory state, and also we want to prevent the collection of traces by means of instrumentation tools like Valgrind, for example. Essentially what we need is an anti-debugging technique. Now, for anti-debugging, multiple options exist. The first option is to let a program check the environment for the presence of a debugger. For example, the program can query the operating system via numerous system calls. However, in practice, it's not that hard for a debugger to intervene and to fool the process that is checking the environment. So this is not a good option. In practice, this has been demonstrated not to be very strong. So we focus on a second option, and that is to prevent a debugger to attach in the first place. We're not going to allow it to attach and then try to detect that. We're going to prevent it in the first place. The reason we can do so is that typical OSs, well, actually all OSs we are aware of, and hardware support to make debugging more efficient, support at most one debugger per process. It's not possible to attach more than one debugger. So there is actually only one seat for a debugger, and what we will do is we will occupy that seat with a custom debugger process. On top, we will make the control and data flow of the application dependent on the presence of that custom debugger. This way, we will prevent that an attacker can detach the custom debugger. In essence, what we want to do is to provide an anti-debugging protection by means of a self-debugger. So how does this self-debugging technique work? Well, suppose we have a binary or a library with some functionality that we need to protect. The first thing we do is we inject a mini debugger. And as soon as this binary or library is loaded, what the mini debugger will do is it will fork off a separate process. And so from now on, we have two different processes, two applications running in a separate memory space. And then the mini debugger in the forked off process will attach using the ptrace interface to the original process. And so from now on, the main application is actually a debuggee, and the mini debugger serves as a debugger of that debuggee. Now, of course, if we would stop here, it's trivial for an attacker to detach our mini debugger and to attach his own debugger. So we go further and we actually change the code of the original application. Suppose, for example, that function 2 needs to be protected. What we actually do is we rewrite its code so that it consists of two parts that have to collaborate to provide the original functionality. And in the original program, in the debuggee, at some point we will let the code raise an exception, and this exception will be caught by the mini debugger, who transfers control to function 2 or to its part of function 2. Then some part of the program is executed, and afterwards control is transferred back to the original program. And this can happen multiple times to create a stronger attachment between these two processes. What's new in our technique is that we not only let the control flow pass through the debugger, but we also execute part of the computations of the original program in this separate copy here of function 2 in the debugger. This is not trivial because this code is executing in a separate memory space, so quite some rewriting of the code needs to be performed. For that more advanced rewriting, we rely on the Diablo link-time rewriter that was developed in our labs at Ghent University. Now let's have a look at the provided protection in practice. So in our development VM, I've opened two shells on our development board. As before, this is the ARM Panda board, and we are running, in this case, Linux. Now, if we look at the software for this demo, you see a program, simple demo. This is a program that will generate a software license, and to do so, the license management happens in a library to be protected. This is from one of our project use cases, and you see in directory BC02 we have the unprotected library. In directory BC05 we have a protected library. In this case, the protected one is much smaller because we've stripped it from symbol information. Now, one of the things I can do, for example, I can run this simple program with the unprotected library, and if I do so, this program prints the license key that it generates, but it also waits for a key so that I can show which process is actually running. If I then on the board in the other shell look for the process, you see that one copy of this process is running. Okay. Now, if instead of the unprotected library, I use the protected library, and again I'm gonna check which processes are running. Now you see that actually two processes are running. One, of course, is the debugger, and the other is the debuggee. And you see that the program is just waiting. So that's as expected. Now let's check, for example, what happens if we try to debug this program with GDB. So I'm going to start the, let's start with the unprotected program. If I load it in GDB and I just run it, then everything just works out of the box, no problem. However, if with GDB I try to debug the protected version, in this case you see that the program does not execute like it should, and the problem is, of course, that the process that is forked off cannot attach to the debuggee because GDB is already attached to it. So running this program in GDB does not work. Now if I interrupt the program and I instruct the program to follow the child process, then if I run the program and restart it, you see that it works, but now I'm not debugging the debuggee of my self-debugging program version, but I'm actually debugging the debugger. So I cannot observe the internal operation of the main program. I can only observe the internal operation of our mini debugger. And that's of course the case because in our current protection, the debuggee does not yet debug the debugger. We don't have circular debugging yet. Now I can also show what happens if we try to attach GDB afterwards. So let me start the program first, the unprotected one. And then again, let's look at the process numbers. There's only one process, and with GDB I can attach to this running process without problems. This succeeds and I've attached, no problem. However, if I launch a protected program and then I look at the processes, again I see two of them. Now if I try to connect to the second one, that will work out of the box again, because with GDB I am now trying to debug the debugger of our program. However, if I try to attach to the first process, so 6909, what you see is that GDB fails to attach because only one process can p-trace another, and the debugger of our protection is already attached to the main process. Finally, let's have a look at a program like strace, which is used to dump a log of all the system calls that a program makes. And again, first we'll look at a program where we use the unprotected library version. In this case, we see the whole log, and for example, we see that the string "press any key to continue" is written. You see it printed on screen in the middle of this log actually, and we can simply press a key and continue. Another thing you could see is the license key that's printed here. Now let's try again, but instead of the unprotected library, let's use a protected library. If we do that now, you see that at some point strace fails and the process stops executing, and the reason is of course that strace was already attached to the main process, so our forked off debugger could not attach anymore, and hence the application stopped executing. So all in all, you see that this protection is quite effective to defend against tools like GDB and strace that depend on the p-trace interface. This video, along with all the research that led up to it, was sponsored by the European Union 7 Framework Program.